Let's move on to our main presentation. Here's Sage Weil to talk about Ceph, an open source distributed storage system. Okay.
My name is Sage Weil. I'm working on the Ceph distributed file system for the last several years. This came out of my graduate work at University of California in Santa Cruz. My research was sponsored by the Department of Energy. Building these massive supercomputers, they had problems with their metadata workflows in particular, where they had tens of thousands of nodes trying to write files to the same directory or to write data to the same file, and their storage systems just don't scale. So that was sort of the original motivation behind this work. But I found that by solving a problem specific to their issues, ended up building something much more general and useful for really all kinds of workloads. So what is Ceph? It is a scalable storage system, anywhere from one node to thousands of nodes, gigabytes to exabytes. The system is designed to be reliable with no single points of failure. All data in the system is replicated across multiple nodes because when you build a system this large, failure is a norm rather than the exception. The system is designed to be self-healing so that when nodes go down, the system re-replicates data around it automatically to deal with that failure. And it's designed to be self-managing because when you're dealing with 1,000 nodes, you don't want to have 1,000 administrators swapping up, managing that software. So the Ceph storage system provides a number of different interfaces, a number of different ways you can actually access that storage. Sort of at the highest level, there's a distributed file system that gives you POSIX semantics, files and directories, sort of the usual interface. There's also RBD, which is the Rados block device. This is a thinly provisioned snapshotable virtual disk, think iSCSI, but on a cluster. There's a Linux kernel driver for that, and upstream in Linux, there's also native support in QEMU and KVM. Think of your virtual machine that talks directly to your virtual disk stored in the cluster. There's Rados Gateway, which is a RESTful object storage proxy, and it provides an S3 and Swift compatible RESTful storage interface. And then there's librados, which is a low-level driver that gives you direct access to sort of the low-level storage infrastructure that underpins the entire system. So what makes it different from other systems that you may have encountered? First and foremost, the system is open source. It's licensed under the LGPL2. The development is completely open. Copyright is shared, distributed among multiple organizations, so there's no one company that's sort of holding the project hostage. The system is designed to be flexible. It's designed to be deployed on commodity hardware with incremental scalability, so you add storage nodes as you need more capacity. With modular server components, so the storage system is just a series of daemons running on all these servers, talking to their local disk. There are multiple storage APIs, different ways you can talk to your storage. And we try to avoid legacy design anti-patterns. So we try to avoid block-based interfaces that have sort of made sense 30 years ago and make less sense today when you're talking about systems that are distributed across lots and lots of storage nodes. We want to avoid any kind of manual workload partition. You don't want to have an administrator that's telling the system to move data from one server to another. The system should do all that work for you automatically. And we want to avoid the idea of having passive servers. That is, servers that sit on the network waiting for commands but don't actually do any useful work while they're sitting idle. All of our storage systems these days are computers. They have memory and CPUs. They can actually think for themselves to some degree, and we want to try to exploit that. So at a high level, what I'm going to talk about, the object storage abstraction that sort of forms the basis of the system. Sort of a design question of where do you decide where to store data in the system? Assuming you have this distributed cluster over hundreds of nodes, how do you decide where to put your data? How we make that cluster of hundreds of nodes self-managing, how the nodes actually work together to behave sanely. And finally, how we build a POSIX file system on top of that abstraction. So to start out, what are objects? An object is really just a lump of data. It has an alphanumeric name, some blob of data, kind of like a file, and some named attributes, or extended attributes, I guess you could call them. We separate the object storage cloud, I guess, into separate pools. So each pool is a separate namespace, a collection of objects, essentially, and has some basic properties, like the level of replication that we want for those objects, whether it's 2 times, 3 times, 4 times, whatever. what kind of allocation policy we want. Maybe we want these replicas, the first replica to be stored on fast disks and the second 2 replicas to be on slow disks or whatever. So that's sort of handled at a pool granularity. And then sort of behind the scenes, there's actually a cluster of servers that are managing all this, actually storing these objects, which we refer to as RADOS, which is a Reliable Autonomic Distributed Object Store. That's the software that sort of builds this object storage abstraction that lets you just shovel lots of data into it. And that's a low-level storage infrastructure that underpins the entire system. So there's this librados library that lets you talk directly to this basic storage abstraction of just pools and objects. Rados Gateway is sort of a thin layer in front of it that gives you a RESTful interface that's compatible with S3 or and then on top of that, we build other storage abstractions like a Rados block device and a distributed file system, all based on this basic storage idea. So one of the basic questions when you're building a distributed system like this is how do you decide where to put your data? So the simplest approach is just to remember where you put it. I stored data A on node B in file C. The problem with that approach is that the system, once you do that, it can't move the data somewhere else because then you won't be able to find it. Because if you remember where it is, the system has to keep it in that place so you can go find it later. A different approach is to name the object and have the system track the location of that object. So you would ask the system, say, where is object A? And it would tell you, go over here, and then you go to that location and you'd read the data. That's better because the system can move the data around to balance data and to recover from failures and deal with all the things that happen in the cluster. But it still sucks because the system has to maintain this mapping of these are the names of the objects and these are the locations where they're stored. And as you start to build a system that has billions of objects across hundreds of nodes, that index, that directory, becomes hard to scale. So a third approach, a little bit more tricky, is to calculate a pseudo-random mapping. So the idea here is that you take the name of the object and the set of nodes that comprise the cluster, and you feed that into some magic function, and out it spits out the current location of the data, or the location where that data should be stored. The nice thing about this approach is that you don't have to store a directory at all. You just give it the name of whatever the object is called or would be called if you're going to store it, and what the nodes are in the cluster, and it spits out where it should be stored. The algorithm that we use to do this is called crush. So the key things about crush to remember are, first of all, that it's functional. So you give it some input, x, it's an integer, it's derived from whatever the name of the object is, and it spits out the nodes where you should store that data. And this gives you a pseudo-random uniform distribution. So all your objects are randomly scattered across the storage nodes and balanced. So you can weight the nodes. Say this node is twice as big as that one, and it'll get twice as many objects. But aside from that, it's totally random distribution. The nice thing is that it's a fast placement calculation. So a fast calculation to decide where to store your data. Another key thing is that it's a stable mapping. So if you have 99 servers and you have a whole bunch of data in there and you add one more, then 1/99th of that data is going to move to the new server, and you're not going to have some sort of like reshuffling that you get with the sort of naive hash function. And the other key feature that distinguishes Crush from similar approaches, there's an algorithm called consistent hashing that a lot of these systems use. What makes Crush different is that it has features that allow you to handle reliability a bit more intelligently. So the idea is that you describe the cluster in terms of the physical architecture. So in practice, you have a data center, you have rows of cabinets. In each cabinet, you have a series of nodes, and in each node, you have a series of disks. And so you just describe your storage array in terms of this hierarchy, and then you describe a placement policy in terms of that hierarchy. So you might say, I want 3 replicas. I want all of them to be in the same row so that when I replicate them across multiple nodes, I don't saturate my core switches. But I want them to be separated across different racks so that if I lose a single power circuit, I only take out a single replica of my data, and the rest of the system will stay online. And Crush lets you do that while still being a simple calculation that's fast and efficient. And
are those relationships kind of customizable? Can you?
Yes.
So there's a concept of like a region, a state, or a region.
Yeah. So you construct an arbitrary hierarchy with whatever labels you want to call it. Like usually it's like node, rack, cabinet, whatever. Mm-hmm. But you can do whatever you want. And then you write a policy, a placement rule that says, take one row, pick 3 racks, and then pick disks in each of those racks. And that's where it's data. So sort of a more detailed picture of how Crush actually puts data in the cluster. So what the system will do typically is take a file or a block device, whatever it is, and it'll stripe it over multiple objects. By default, objects are formatted, but you can specify put whatever parameters in there that you want. And then each object is mapped into what we call a placement group, just a sort of arbitrary collection of objects. It's kind of like a shard if you're used to talking about distributed databases or something like that. And then each placement group or collection of objects is mapped to a set of OSDs that are going to replicate all of those objects using this crush function. And this gives you a pseudo-random uniform distribution of data across the cluster. So the key things that are great here is that first, it's a fast calculation in order to look up data. We don't maintain any directory that says where the data is stored. We just calculate the location. It's reliable because we can specify that our replicas are separated across failure domains, racks usually. And it's stable, so that when we add or remove devices, a small number of objects move around in order to redistribute things evenly across all nodes and sort of maximally utilize our available hardware resources. So sort of taking a step back here, what do we typically mean when we talk about a storage cluster or a storage system? Well, in the past, usually people were talking about SANs, fiber channel network. They're usually talking about storage in terms of ones, or maybe a SAN file system if you're a little bit more fancy. But essentially, these are expensive and, frankly, antiquated designs and systems, especially expensive. Today, things are typically a little bit different. Things are moving more towards NAS, so people have servers on the network that storage is deployed in terms of rack-mount devices that are just computers. With Ethernet, typically, we use higher-level protocols like iSCSI, NFS, CIFS over IP to talk to them. So the situation has changed a little bit. Now we're talking to general-purpose computers on the network, but these storage servers are still passive. Even though our storage servers have CPUs, memory, they're running arbitrary software, they can do all kinds of crazy things. They just sit there until you say, read this block, and then they read that block, and write that, whatever. They're not doing very much work on their own. And so what Ceph tries to do is sort of leverage that intelligence to do something a little bit more intelligent. So Ceph storage nodes typically consist of two pieces. There's the object storage daemon, the OSD, and then that sits in front of a local file system, usually Btrfs, on one or more disks. And each one of these participates in the overall storage cluster. And the difference is that these daemons actively collaborate with their peers. They'll talk over the network to read and write data, true, just like any other system, but they'll also talk to their peers in order to do useful work, like replicating our data, all data in systems replicated n times, to consistently apply updates. So if you write to an object, it'll write to all copies of the object consistently and make sure that those copies are in sync and covered. The daemons will detect node failures if there's any kind of failure in the system, and they'll also work to migrate data if there's a topology change. So when you add new nodes to the system, there's more storage available. Those daemons will talk to each other to manage the migration of objects to those new disks in order to rebalance the data. And the thing that makes this work is this idea of functional object placement. So there's a small data structure called an OSD map that completely specifies the placement of all data in the system. It basically has the cluster membership, what the nodes are that are participating, what their IP addresses are. And it has this crush function that maps objects, placement groups to those OSDs. And because every node in the system has a copy of this small data structure, every node in the system knows where all the data should be located. So it can look at all the data it currently has and says, should it still be here or should it be somewhere else? And when it's talking to another node, they can say, well, we have the same copy of the map, so we know that we're on the same page and we can do things like replicate, migrate, those sorts of things. And what this mostly comes down to is this process that we call peering. So whenever the OSD daemon starts up, or whenever there's a topology change, whenever there's a map update, they go through this identical process where they look at all the data that they currently have and recalculate its mapping to make sure it either should still be stored where it is or where it should go. And then they coordinate with each other to actually move the data to the correct location.
So are the maps like version? Do they have like
Yes.
a timestamp?
There's a version number, epoch, and a timestamp. And then whenever there's an update, the sort of cluster controller will publish a diff, basically, with a new map, and that'll get sort of distributed throughout the cluster, and then they'll resynchronize. Exactly. And this is an identical process is followed for any kind of change. So it could be that the node failed. It could be that we expanded the cluster by adding storage nodes and remove them. Maybe we decided we wanted to replicate 4 times instead of 2 times. Whatever it is, when any arbitrary change to that map structure, the nodes will talk to each other, coordinate it, figure out where the data should be stored, and then they'll actually make it happen. They'll start copying data. Much easier for the administrator to manage. So we usually use Butterfest underneath these Ceph storage channels. You can actually use any file system, but we prefer Butterfest. So the question is why? Sort of the new Linux file system. But mainly it's because Butterfest is very featureful. It's got lots of great things in it that we want. So first, it's a copy on write file system, which means that you can make efficient clones of files. It's always consistent on disk, so if Butterfest crashes and it starts up, it never has to do an FS check because the state on disk is always in a perfect coherent state. It does snapshots, it does checksumming throughout. Whenever it reads data, it verifies the checksum and makes sure it's actually what it expected to find there. It handles multiple devices, much like ZFS does, so you set up pools of storage and it'll replicate internally, that sort of stuff. It has transparent inline compression, online scrub repair, cute name, all that good stuff. But beyond that sort of basic functionality, Ceph actually integrates with Butterfest pretty closely. So we hook into the Butterfest's internal transaction subsystem in order to manage the way that the storage daemon commits data to disk. So it always makes sure that the stored data that it's storing locally is coherent with other copies, and they can take advantage of that. We hook into the copy on write infrastructure so that when the snapshots happen in a sort of higher level distributed file system or via the object interface, we can clone files efficiently without actually copying data. Things like that. So you can also run it on top of ext3 or 4, XFS, or somebody just submitted a FreeBSD port that I haven't tested.
A FreeBSD, we're using ZFS? Or
it doesn't matter. You can use whatever file system underneath that you want. So eventually,
but if you use Butterfs, you get those kind of transactions and the snapshot and clone aware type functionality.
Right. So they haven't done any work like that integrating closely. I didn't know that ZFS is available on FreeBSD.
Yeah, since FreeBSD 7 or something like that. Yeah, so they're.
So that would be a useful thing for them to do probably as the next step. But they just got it working last week, I think.
Cool.
So that's sort of the cluster that stores all these objects. So there are a number of ways that you can talk to it. At the lowest levels, you can use Liberatus to talk directly to the object storage cluster. This gives you direct parallel access, so you have a single client node and it's talking to all 1,000 nodes in parallel. You can massive throughput, whatever your network can support. Bazillions of objects across thousands of nodes, and there are bindings for lots of different languages, C, C++, Python, whatever floats your boat. The API gives you some interesting things. In addition to just simple like read object, write object, you can do compound operations. So you can do things like read the object and read these extended attributes, or you can do more complicated things like, this is a write operation, but check this X adder on the object, and if it's set to A or some value, then proceed with the operation, but if it's different, then abort. So you can do sort of a compare and swap atomic thing in the object store. The object storage interface gives you snapshot primitives. So your operations have a sort of a context associated with them that informs how the copy and write stuff happens in the object storage layer. That lets you build sort of higher level snapshot functionality in. There's some stuff to do. Watch and notify is sort of like a lightweight locking mechanism and communications infrastructure that uses the objects as sort of a communications channel. There's a key value interface that lets you store keys and values in an object. And one of the nice things is that the object storage API is extensible. So of course, it's open source. You have the source code. You can do whatever you want with it. But sort of beyond that, we have this plugin infrastructure that lets you define your own classes. So at the sort of the base level, the system implements your basic interfaces for objects. You can read data from them, write data. You can get set attributes. You can delete them. That's sort of the file-like basic functionality. But you can also dynamically load classes into the cluster that do build new functionality on top of those basic methods. So for example, you could link in a crypto library and build a class that would calculate a SHA-1 of an object and return you just the result. Or you could link in an image library and have it rotate an image or resize it and then save the result without having to read the object data over the network, change it, and then write it back again. So the basic goal then is that you can move the computation to your data. So typically in these systems, say you're building Flickr or something, you've got a massive collection of images. You have to do something to them, right? So you want to resize all your images or remove red eye or something. You can do that on the storage node without actually incurring the network load to do all this stuff. And the metadata server that's used for the file system and stuff actually uses this functionality as well. So it has a class that stores directories in objects, and so it can send a command to the object store that says, remove this one directory entry from this object that represents the directory contents. And the object store will do that work for it instead of having to read the entire directory of the network, make a small change, and then write it out again. Let's see, one of the other pieces is there's this a RESTful object storage Rados gateway system, and that's essentially a proxy. It's actually a fast CGI process that talks to Apache or Nginx or whatever, and then links to Librius on the back end and talks to the storage cluster. And that gives you sort of a standard HTTP RESTful interface to an object store on the back end. So it's compatible with S3 and with Swift. So that's something that some people like. Probably one of the more interesting pieces is the Rados block device, which is essentially a virtual disk image that's backed by, it's like takes a block device and it just stripes it over objects. Kind of like you take a file and stripe it over objects. But the key thing is that it basically puts this virtual disk image in the cloud, in the cluster, and the single disk image is striped over all 1,000 servers, 100 servers, however big your cluster is. And it lets you do really cool things. Instead of having your virtual machine tied to the virtual machine host and this local disk that you hope doesn't fail, it's stored in the cloud and it's replicated and it's high performance and it's always available. You can do cute things like live migration of virtual machines between hosts, for example, which even, you can do a KVM and KVM linker, and it'll just magically move around. The block devices are thinly provisioned, so it doesn't actually use the storage until you write to those regions of the block device. You get per image snapshots, so for each VM image you can create read-only snapshots and you can back up space on that, delete and so forth.
I assume cloning too, right?
So that's what this layering is.
Okay.
So this is actually something that we're working on right now. And that basic idea there is that you have a virtual machine image that's Ubuntu 10.10. That's your gold image for this class of virtual machine. And whenever you want to create a new virtual machine image, you just create a layer, a clone of it on top of it, and the reads that fall through the new image will come out of the old one, and But essentially, the goal is to do instant virtual machine image creation, essentially. So instead of having to wait for that image to actually be copied to the host and create a duplicate, it'll instantaneously create a sort of a layer on top of it.
Kind of like ZFS does snapshots?
Yeah, essentially.
So the clone is a writable snapshot. Right?
Yes, right. So this creates a writable layer on top of a read-only image.
Yet you're only changing the blocks, the objects, the parts of the objects that change.
Right.
So you could you need another one of these web servers here. Let me give you one. Boom, it's ready to go. And here's two more, and they're all unique. You can do individual customization each one after that. Yeah, that's cool.
Yeah. So the idea here is that I should call it cloning instead of layering. Layering is how it's actually going to work. But the idea is to do this. That's one use case where you have a gold image and you want to create clone images. Another use case would be that you have an image that's stored in this particular pool of the cluster. It's stored over here, and you want to migrate it to this other pool of the cluster somewhere over there. And so you can create a layer, essentially create a clone in the other location, and all the I/O will fall through to the old location until you sort of asynchronously in the background migrate all the data.
So you can use that not only to get to another physical location, but you can use that to migrate to different types of storage as well.
Right, exactly. Yes. So the goal is to make something that's sort of general purpose, and it'll.
But yet you can. So the new change data will come through the newer, faster stuff. And then read through to the older.
Right. So you'll take a performance hit in the meantime.
Yeah, but as things move over, you get moved to the newer, faster, new hotness. Everything goes faster.
Exactly.
Cool.
That's the plan. So RBD is actually very simple. It's a simple layer on top of the object store, assuming you have this like magical, scalable, reliable object storage system. Then RBD is relatively simple, I guess. So there's native QEMU KVM support via the user space library that is linked directly into the QEMU binary source code. So you can launch a KVM virtual machine with the right build options and the right magic string for your image, and it'll talk directly to the storage cluster without any kernel support, without any social stuff, and it'll show up indistinguishable from any other disk. So that's nice. There's also a Linux kernel driver, so you can echo a magic string to the sysfs file, or you can use the command line tool. It'll do it for you to map an image, and it shows up as a regular Linux block device that's indistinguishable from any other block device, but it's backed by the source cluster, similar to iSCSI or whatever else. You can run whatever file system you want on top of it. We've worked on the integration with libvirt and OpenStack. So libvirt will launch KVM virtual machines back with RBD images, and all the authentication stuff passes through magically. And there's there's a command line utility that lets you administer. You can create images, resize them, create snapshots, delete them, roll back snapshots, all the usual stuff you'd expect out of a storage system managing block devices. So sort of the last big thing then is on top of this, the original goal of building this whole system was to build a file system, right? My original research was actually focusing on building a metadata server that would manage a hierarchical POSIX namespace of billions of files, petabytes of data. And so the goal then is to create a POSIX file system on top of this basic object storage abstraction. And we do this with a series of metadata server daemons, MDS daemons. So the nice thing about these daemons is, first of all, there's no local storage. So all the data that the metadata servers manage to manage the namespace is just stored as objects in the storage cluster. So there's really one storage infrastructure that underpins the whole system. So really all these daemons need are lots of RAM. They're kind of acting as like a large distributed coherent cache of the file system namespace so that your metadata operations are efficient. And then they're eventually backing that by these objects stored in the object store that are, again, replicated and reliable and all that stuff. And it's a dynamic cluster. So you might just have one metadata server if you have a big file system, or you might have 100 if you have a huge system. It can really, whatever fits the bill, right? You can start up new daemons and they'll add themselves into the cluster, and if you want to shut them down, you tell them to export their load to somebody else, and then they'll gracefully leave. And then the cluster magically load balances for you. So a simple example of how the metadata server sort of works, it's managing just the namespace, not the file data. So if you guys are familiar with Lustre and the Lustre architecture, it's sort of similar to that, or if you've read the Google file system paper, similar to that too. The basic idea is that you have a client, a happy client, and there's some process that opens the file, foo/bar. So it'll send a request or a series of requests to the metadata server to sort of traverse the file system namespace. It'll say, I want to open foo, and the metadata server will have that in its cache because the metadata server has lots of RAM, and hopefully this isn't the first time you've ever looked at this file. But if it doesn't, then it'll talk to the object store and it'll load that directory off disk and into its cache, and then it'll be there for future use. And then it'll issue a capability back to the client. It essentially says, you, client, are allowed to read the data in this file. And from that point forward, whenever the client reads or writes data, it just talks directly to the object store. It knows what object the file is going to be stored in. It's basically based on the inode number. It has a fixed name, and so it can calculate the location of the data, go directly to the storage node that has that data, and read and write it. And then when the process closes the file, it relinquishes the capability back to the metadata. At a high level, there's actually more going on than this. So the key things here are first that the metadata server is not in the I/O path. So in contrast to an NFS server, where all of your metadata workload and all your reads and writes, all that stuff is funneled through one big node that you hope is very fast and doesn't scale. In contrast, here the metadata server is handling only the metadata workload. So it only opens and closes and unlinked and renames and stuff like that. And all your actual file I/O, which is the bulk of the data transfer, goes directly to the storage node that's balanced across these 100 servers or whatever.
Now, is the file system presented in the same way you can mount an NFS file system?
Yes.
Okay.
Mount -t Ceph, the cluster manager IP / whatever. Yeah.
Is permission to it also managed the same way, like through an export FS?
Yeah, it's a little bit different. But yeah, it works kind of like Kerberos, but you have a crypto key that you use to mount. It says I'm allowed to mount the file system, and there's a capability that says this node is allowed to mount the file system, basically.
How's the key management handled with that?
Through a command line utility. It's master there. It's similar to Kerberos, but it's simple. It's very simple. So the question then is, how do you have this hierarchical namespace for your whole file system, and say you have 10 metadata servers. How do you distribute this namespace across 10 metadata servers in the same way? And if you just sort of take a step back and look at all the design options, there's a spectrum of options. So you could have a very coarse partition. You could have a static subtree partition, which is what people who manage farms of NFS servers are used to. /home/ all the A's are on this server, and all the B's are on this server, and all the C's are over there. And then when you get too many C's, because that's a popular letter, you split them up and you manually migrate them over to this other server. But there's that. So the advantage there with this sort of coarse coarse partition is that entire hierarchies are stored in a single server node. And that's good because workloads tend to be, metadata workloads tend to have a high degree of locality. So if you're talking to one file, you're usually interacting with files near it in the file system namespace, and that means you're talking to the same server, the caches are warm, and all that good stuff, so it will perform well. On the other hand, there's a high management overhead in terms of actually making sure your servers are balanced. As anybody who's managed to farm and test servers can tell you, it's sort of a nightmare. On the other hand, at the other end of the spectrum, you can use, some systems use hashing techniques. So you might take the directory inode or the file inode and you feed it through a hash function that gives you a random server. And that gives you very good balancing because you're basically randomly scattering all the files across the cluster. And that gives you a really good load balance, right? Because you don't have any sort of hotspots. If you have one home directory that's getting a lot of traffic, it's distributed across the whole cluster. So that's good. But on the other hand, you're destroying locality because you basically completely ignore the namespace, which gives you all this great information about what the user is probably going to do. So what Ceph tries to do is sort of capture the benefits of this entire spectrum. Think big. So what we do is what we call dynamic step-tree partitioning. So the load balancer inside the metadata server essentially looks at what the workload temperature is of the entire hierarchy. And it sort of dynamically takes pieces of the subtree and maps it to different servers, depending on what the workload is. So in this picture, each different color is a different metadata server, and you can sort of arbitrarily carve up that hierarchy across different nodes. The system does this automatically. And so, as if you have, so depending on how busy different directories are, it'll get mapped to different nodes in order to balance the workload, right? And if you have a single directory, even that is extremely hot, so you have a really large directory or you have a directory that has lots of access to it, then you can also take that individual directory and break it into fragments, and then take those fragments and distribute those across multiple nodes. So it can still sort of distribute. So that gives you all the benefits of hashing, be able to distribute these hotspots, while at the same time, most of the time, having a relatively coarse subtree partition. So this is scalable because we can arbitrarily carve up the hierarchy across the cluster. And it's also adaptive because as the workload changes, based on the time of day or whatever, maybe you have an HPC cluster that does a compute on this part of the hierarchy and then moves over here. The system will notice that and it will dynamically redistribute the metadata workload across all available servers so that at all times it tries to utilize all servers to their maximum extent. So a picture of what this looks like. This is an experiment we ran when I was working on my thesis, I guess 4 years ago now. So in this case, before time 300, times on the x-axis before 300, the system was doing something, I don't remember what it was. Running some workload and it was balanced across the cluster. And then at time 300, everything stopped. I shut down the old job and started a new job, which was a whole bunch of processes, all creating a mess of files and directories, off the root directory, dir1, dir2, whatever. So it took a second. Initially, only the red metadata server was doing any work because that was the one that was responsible for that directory. But then it realized that it was busy and everybody else was idle. So it took that part of the hierarchy and broke it up into pieces and redistributed it across all the cluster. So again, the throughput comes up because we're using all servers. Around time 360, we add 2 new servers to the mix just because we can. And the throughput again goes up. And then at time 450, we have another workload shift. This time, that old job shuts down and a bunch of new processes start up. This time, they're all creating files in the same directory. And again, only that one node is busy for a few seconds while all the clients are hitting that one node. And then the load balancer notices that it's busy and nobody else is, and so it takes that directory, breaks it into fragments, and then distributes those fragments across the cluster, and then again you have your throughput going through, so you're sort of maximally utilizing the entire cluster, even though your workload is sort of focused in one location. So one of the other interesting things that the font always gets screwed up on the slide, that the cluster does, so because we implemented a sort of metadata hierarchy from scratch, we could do some interesting things. So one of the things is that we maintain recursive counts of files, directories, and file sizes across the entire hierarchy. So there's like an R size value essentially for any directory that's defined as a summation of all file sizes in that directory and nested underneath it in the hierarchy. And by default, when you do an ls-al, instead of giving you a meaningless number for the size of the directory, it gives you that recursive size. So you can do an ls and essentially get what you would get from a du. So in this case, you can see that top directory has 9.6 terabytes of data in it. And if you dump the extended attributes, you can also see the other things. It has 39 files, it has nested beneath it. You get the file count, you get the recursive C time, so that's the most recent modification within that part of the hierarchy. So that's great if you're trying to figure out why your file system is filling up. You can just do an ls in the root directory and you can immediately see where all your data is stored. It also gives you fine-grained snapshots. So sort of one of the challenges with having a petabyte scale file system that's distributed across hundreds of nodes is that you're probably going to be storing lots of different types of data in there, and you're not going to have sort of the same data retention backup policies for all that data. So having a global snapshot of the entire file system doesn't necessarily make a lot of sense. And so what we give you is the ability to snapshot arbitrary subtrees or subdirectories of the system. And we give you a simple interface to it. So there's a hidden .snap directory in every directory. And if you do a make dir in that hidden directory, then it'll create a snapshot right there. And you can CD into it just like you can with the NetApp hidden .snapshot directory. And do whatever you want with it. And then if you do an render on that snapshot directory, it'll go away. And then, yeah. And this is all, when you create a snapshot in the file system, it leverages sort of the copy on write stuff under the covers in Butterfest to actually make that efficient. So it only copies data when you actually modify it, and it's all smart. So there are a number of different ways you can talk to the file system. There's obviously the client side that's talking to the server. The goal is to give POSIX semantics with strong consistency. So the standard is essentially that processes that are interacting on different hosts with the file system should have the exact same results as if they were on the same machine interacting with the file system. So in contrast to NFS, which gives you really weak consistency and tends to screw up files if you have them interacting with the same files, Ceph tries not to do that. It tries to give you sort of consistent behavior. And in order to do that, the clients maintain consistent metadata and data caches, and there's lots of blocking and leasing going on when they're talking to the metadata server to make sure that when you actually read data, it's actually the correct answer that's given back. There's a Linux kernel client implementation that's been upstream in Linux for, I think, 5 or 6 kernel versions now. That works in the usual way. You probe the module and do a mount-t Ceph, give it the IP address, and it mounts like a normal file system. And then talks to all the metadata servers, all the storage nodes, all in the back end. There's also a user space client implementation. So there's a Fuse client that'll use the Fuse interface. That also works just fine, it's just slower. There's a libceph library that you can link into applications that'll sort of talk directly to the storage system in user space. There are also glue layers that link into Samba. Samba has a VFS abstraction layer. It'll link directly into Samba, so Samba will talk directly to the storage cluster. NFS Ganesha is a user space NFS server that has a plugin for Ceph as well. And there's also a shim for the Hadoop file system, so that if you're familiar with Hadoop's MapReduce system, whatever, it'll also talk directly to Ceph. So you don't have to have kernel support. So that's good. I don't even know how up to date this is. So yeah, the Linux client has been upstream for a long time. RBD has been upstream for a long time. You can take a recent Linux distribution and it'll actually work. And there are build packages for the usual. Somebody just submitted a FreeBSD port, so that's exciting. The real focus these days is on stability, so making this actually work reliably enough that you can actually use it in production. And we're getting closer. We're focusing at the bottom of the stack first to make sure that the object storage nodes that actually manage the objects are rock solid and aren't going to lose any data. And then we'll work our way up to the RBD block device layer, sort of the virtualization use case, and then up to the file system. This talk is from a 12 conference, so it's all written in C++ and some C. We use Python for QA stuff. We built a whole system we call Topology, which is our QA harness that we manage. Essentially, automatically spins up small clusters and runs a series of tests, and then gathers all the results and makes sure there are no errors, and then shuts it down again. Uses this for automated QA. So it works. That's basically it. We have a web page. It's all open source. The source code is on GitHub now because it's easy and convenient. And mostly what we do these days is work on our QA and our testing and try to find developers because it turns out that's pretty hard to do. People are qualified.
Is it in production?
We are about to launch a production cluster with a user-facing product. So sometime in the next month or two.
Almost.
Almost there, yeah. It's been almost there for a long time, but I think it's actually almost there.
Yeah,
Yeah. So I think actually what we most need is people to bang on it. So if you guys have, test machines at work, if you're interested in trying out something new, it's great to have people hammer on it on a wide variety of systems and find all the weird failure cases that we never dreamt of when you're using.
Yeah, the fun implementation might be using it with the RBD module to
Yeah.
provide storage
Yeah.
for the KVM load. So
Yes.
you're
So-
putting it in development and you're assuming all your code's checked into your source code repository anyway. So that reduces some of the risk and it adds the possibility to add more storage and maybe get some performance out of it and kick the tires.
The whole cloud use case is actually where we get most of our interest these days. Even though RBD is kind of one of the simplest things you can do with the system, it's just a dumb block device. There's this antiquated way of talking to storage. That's what most people want, and that's what they need for building their own private clouds and spinning up all these virtual machines. Each virtual machine just wants a virtual disk that it can put, NTFS or HC3 or whatever your random file on top of.
If you threw together a 10-box object file system now and ran a Ceph file system on top of that, what are the odds that it would just run for, that you get your data back? I mean, is it
It depends on what you do with it. So if you're going to use it just for something like RBD and storing KVM images,
right?
Then it's probably going to work really well for you. I'm not going to make any promises. Make sure you back up your data first because this is still a system in development. But on the other hand, if you're thinking, like distributed metadata server and massively scalable whatever, and you start installing, 5 metadata servers, and you start creating snapshots in every directory, and you start copying stuff around, and you're gonna hit a lot more hairy cases than sort of with those simpler use cases. So it kind of depends. There's one user that I talked to recently who he was testing Ceph. He's been testing Ceph for a long time actually, and somebody in his company asked him for a virtual machine, and he's like, well, he's asking me. He assumed it was because he wanted to try out a virtual machine on Ceph, and so he created it, and not realizing that the person was just asking the wrong person in the organization. It was like for a production node. It was for their wiki or code management or something like that. But it's been running happily for 6 months now without any problems. So.
It's a happy.
Not really good, whatever.
Is there anyone in the HPC environment that's currently using it in production?
Nobody's using it yet. There's a guy at Sandia who's doing a lot of testing on one of their clusters, and all the HPC guys are really interested. The problem with them is that they need to work right now, and they already have invested so much time and energy into making cluster work that it's hard for them to dedicate resources.
I'm jumping in that environment. We currently are NFS backed.
Okay.
Just a fairly small 34 node cluster, but I think I've got some old hardware lying around. Will it run on 32-bit hardware?
Yes. You have to be a little bit more careful with memory usage because you only have 4 gigs of address space, but yeah, it'll work. Yeah, it's all the encoding and on-wire stuff is all Indian safe or whatever, so you can talk between big Indian and little Indian machines between 30-bit and 64-bit. It'll all work, so it just won't be as fast.
Well, I covered this, but if I lose a machine and reputation.
Yeah, so the assumption is that if you have any sort of big system, it's not if you lose a machine, it's when you lose a machine.
Let's put it this way, what if I were to run some Spock instances on Amazon?
Then it probably won't perform very well because your instances aren't going to be very close to each other. They're going to be talking over their own network.
You can build them all in one.
You can. Availability on the same disk, not on the same time. Whatever, yeah. It'll work.
Well, let's just say some of them disappear from time to time.
Yeah. So that's what the system is designed to do.
Well, how do you size it then? Like, what's the minimum amount of nodes? Like the object nodes that should be deployed, and I'm sure there's other sizing
Yeah. So there
thoughts for the metadata cluster.
I used to have a slide for that. So there are 3 types of daemons. There's a monitor daemon that manages sort of, it's the cluster monitor who manages sort of cluster membership. It has a master copy of the OSD map and MDS map and so forth. And you can run one of those. It just could fail. So usually you want to do 3. It runs Paxo, so you want to have an odd number of nodes essentially. And then there's the OSD daemon, which stores objects, and you can have any number of those you want. You can have 1 of them, and it just won't replicate, or you can have 1,000 of them, and you'll have this massive system. And then metadata servers, you can have 1 to 100 or whatever.
And you only need the metadata server if you're
If you're
doing
using
the
the file.
POSIX file system.
Exactly, yes. So our production cluster that we're going to be rolling out initially won't have a metadata server, it's just objects.
You're doing an object store. And the other one is if you say so like you're the kind of the tire kicker guide, you could start with the object store, say you're serving up KVM images for your development team.
Yeah.
Then, and then you can also, then maybe if that's working pretty stable, then you could stand up the metadata stuff to add additional POSIX file systems, maybe for related or other work.
Right.
And you could just blend, you could just point the metadata servers into the object store.
Right.
Could that happen all live? And they can all share the same data?
So by default, when you build a new file system, it creates 3 pools. One, it creates 2 pools for the file system, the metadata pool and the data pool. Data has the actual file data, and metadata has the directory namespace stuff. And then it creates an RB pool for RB images. But you can create whatever pools you want. And you can either store your objects directly in them, you can create separate RBD pools, you can organize your storage however you want. And they're all, the system is designed so that all these pools of data can coexist in the same system. Just like you're used to with CFS. Yeah.
So if you have, say, various servers, some that are, with slower hardware, some faster hardware, is there any way to like tell the system prefer these over these for storage, like sort of like weight?
Kind of. You can weight those, and that essentially is the relative amount of data that it'll get. So if you have a node with a weight of 1 and one with 2, the 2 node will get twice as much data as the 1 node. But essentially what that means is it gets twice as much data, and then it gets twice as much I/O because it has twice as much of the objects, and everything's random, right?
Is there any kind of support, I'm going to call it tiering, but I got a request today where they want really fast.
On SSDs and then
exactly.
data and then tape or whatever. So there are sort of 2 ways you can do it. You can architect your cluster sort of with that in mind, where you have a series of OSDs that are, SSDs or memory backed using one of those crazy memory cards or something. And then you have a series of OSDs that are using disks. And then you could write a crush rule that says, I want to pick the first replica from the fast nodes and the second 2 replicas from the slow nodes. So you could do that. Alternatively, you could just have uniform nodes, and inside each OSD, it's just talking to a Btrfs file system, and you give Btrfs an SSD and a bunch of slow disks, and you let Btrfs do all its caching stuff. And it doesn't do very much of that right now, but there are a lot of people working on it. Basically, Btrfs is sort of the future Linux file system that's going to do everything that you would ever want to do with file systems: compression, encryption, tiered storage, caching, SSDs, memory, all that stuff. Whatever, yeah.
Is anybody like this kernel mode ZFS stuff is starting to happen? Is anybody looking at using an OSD with that?
I haven't talked to anybody who's tried to wire it up to ZFS, but in principle, it should work reasonably well. So this is actually, so when Sun bought cluster file systems, the guys who made Lustre, Lustre is built on top of the ext3, which turned into ext4. When Sun bought it, they basically said, let's run Lustre on top of ZFS. And so they spent like 3 years basically trying to glue the ZFS DMU, the object layer in ZFS, to the Lustre storage target, and never really shipped it, I don't think. And then it got bought by Oracle, and now they have ditched that. And I think now they're going to put it on top of Btrfs. But in principle, you can do it, right?
You're just not aware of anybody.
I mean, there's a group at Lawrence Livermore actually that took CFS and they ported it to Linux.
That's
what you're talking about.
And that's a kernel mode. It's not the fuse layer. It's a kernel mode implementation.
Exactly, yeah.
So
but it's just they
theoretically
just did the
more
object layer.
performant.
Right.
Yeah. And then the other thing is, how does the OSD and Btrfs, how do they compete for RAM in the kernel? I assume Btrfs, kind of like ZFS, tries to do a lot of RAM caching as well.
So the Btrfs is the kernel file system, and so it has sort of omniscient understanding of what memory is in the system. So it'll use as much RAM as available for its page cache.
Yeah.
And then when user space processes need memory, it'll cause pressure and it'll flush that out. And the
But-
OSD
so-
daemon doesn't actually do any counting. So all it's doing is it's talking over the network, it's arbitrating recovery, and it's processing requests and then feeding it through to files.
Oh, okay.
So the OSD
So it
doesn't
lets
use
the-
that much memory.
It lets the file system do all the caching.
Exactly.
And
yeah.
so it's got a pretty small footprint.
Right.
It's just maybe has a lot of sockets open or whatever
Exactly.
to connect into other nodes.
Exactly. Yeah.
Cool, that's good. What about the map updates? Or like as you scale up, do you have pauses where people are trying to sync up the latest version of the map? And
So,
especially
yeah.
when you're like failing or bringing on new.
So the goal of the map system strategy essentially is to make it so that you don't have to have the latest map. You just have to have a record. Because most of the time when the map changes, it'll say this one node went up or down, and this small amount of data maybe shifted, something happened to it, but most of the time it doesn't matter.
Oh,
So if you have a client,
unless your data center went offline.
right. But if you have a client that says I have map 100 and the server has map 100, then they agree and they'll happily read and write data. And it's only when the client has map 100 and the server says I have 200. Here's the diff. So to bring up to date, you should actually be talking to the server, and that's when you sort of get shifted somewhere else. But all the nodes in the system are comparing versions, and whenever they notice that they have a newer version than somebody else, they'll share the diff. And so any update will sort of propagate throughout the cluster organically, I guess.
Do you guys handle some kind of protocol version? For example, let's say you have a cluster with n amount of nodes, and then you want to update one node to a newer version.
Yeah. So there are a couple different layers of it. There's like a hard protocol that says that different versions won't talk to each other if you have like a serious change in the protocol. But most of the time you have like a small feature that changes or an object that it gets encoded differently. And so all that stuff is versioned, and when two daemons talk to each other, they negotiate the features, and so they can adjust their encoding when they're talking to the other node, so they can all behave. So we've built in all the infrastructure to do this, so that when we make a change, we can make it graceful. The truth is that most of the time now when we make a change, we don't bother because it's a lot of work to actually do it, and there aren't that many users with big clusters that need grid online, and so we're sort of cheating. Yeah. But all the infrastructure is there so that when we do need to do it, then we can actually do it. Yeah.
When you discover one of the remaining error conditions, how do you go about like debugging it for tracking down the file? Like what sort of debugging tools are you using?
We have logs. So all the daemons have this logging level that you can turn way up or way down. If you turn it way up, it gets done lots of crap with the log and it goes really slow. So we'll gather logs. We run things through Valgrind sometimes, which is a sort of a runtime checker that makes sure you don't access uninitialized memory and stuff like that.
Do you run into like kernel panics where the machine's locked up and you can't really see what's
Usually, sometimes, but it's usually Butterfest. So Butterfest crashes on us periodically, and so debug that sort of independently. Ceph isn't doing anything too weird. I mean, it's just reading and writing files, but it still manages to work out a lot of bugs that other people don't hit. So we've hit lots of bugs in ext3 and ext4 actually, because we use extensive use of the X adders, and most people don't change the adders very much. They like set a security label and then they're done. They never touch it again. But we're constantly setting big ones and small ones and stuff. So we've hit some stuff that way. And work with those guys to work out those problems. Yeah, I guess this is it. I mean, we're using, our entire tool chain is open source, right? We're using GCC, we use TC-malloc, which is a replacement for malloc that came out of Google that is way more efficient and faster. And the nice thing is it has a heap profiling tool, so you can flip the switch and it'll keep track of where all your memory allocation sites are going, and then you can tell it to dump. And you can look at this nice directed graph that tells you where all your memory is coming from. So that's kind of cool. We use Crypto++, O-Profile is a profile or something.
Was there some sort of frustration with Luster that led to the development of this?
So the national labs, so this is like 2002, 2003 when the national labs were first starting to really use Luster, and they gave all this money to cluster file systems, and the metadata performance sucked because Luster has a single metadata server, and it doesn't replicate. Yeah, it's basically, Gluster is kind of a hack for HPC, basically, but they never really managed metadata. So most of the research goal was really to solve the metadata problem, and in doing that, I ended up needing to store the metadata somewhere and ended up building the rest of the system.
So it was more or less a response to Gluster.
Yeah.
Just,
More or less, yeah.
what about Gluster? Have you ever
I haven't used it. I know a fair bit about it. Gluster is a very different approach. So it's a series of layers that stack on top of a regular file system. So it's just like there's a layer that will just say distribute across multiple nodes or replicate, or I haven't actually used it, so I can't talk about it in much detail. But it's much simpler. So all your I/O passes directly to the backend server. It isn't as efficient. It doesn't do all the caching stuff. So one of the things that Ceph does with the metadata server layer is it goes to great lengths to cache the client. So what would normally happen, so I had that example where you open a file, you talk to the metadata server, then you talk to the disk, to the OSD. That's actually a very sort of simple and actually not actually accurate picture of things. What would actually happen is the user would cd into a directory, and it'll send a request to the metadata server to like look up, /foo. You cd/foo, look up /foo and look up the inode on the metadata server and get a capability back on the client. And that capability basically says that the inode has a reference to that inode in its cache. And it knows certain things about what the access permissions are and whether they're still accurate or not. And then when you do an ls in that directory, it'll send one request to the metadata server. The metadata server will read that entire directory off disk in one IO, because it's one object. And that includes all the names in the directory and all the inodes and their contents. And then it'll send all that information back to the client. So the client will get essentially a lease on the entire directory and all of its contents. And so if you do an ls-al, it's one request to the metadata server and one request to the disk, and you can list the entire directory. And then if you want to read any of those files, you already got a lease on that inode, and it issued the read capability most of the time because nobody else is writing for the file. And so you can actually read all those files talking directly to the OSDs without talking to the metadata server at all. So things like tar.
through the client kernel module?
Yeah, or libsep, or the user space one, either way. So things like tar go really fast because it's a couple requests on every directory to basically copy the whole directory, and then you just read all the files off the OSDs.
How do you guys deal with, or how's performance when you're having someone, well, first off, how is performance different when you're writing a bunch of little files versus someone writing one really big file? Do you see much of a difference in performance hit?
It's hitting totally different parts of the system. So if you're creating lots of little files, it's lots of IOs back and forth between the metadata server. And so with the metadata servers, each file crate is a request from the metadata server and a reply. And the metadata server is sort of queuing things up and efficiently journaling it out to disk. Whereas if you're writing lots of things to files, it's usually you're writing it to OSDs directly. So they're hitting totally different parts of the system. And depending on what your workload is, usually when you write a bunch of files, you don't actually do an fsync or anything until you're done. And so you can buffer to your heart's content and then flush it all out efficiently and distribute it over the network. Whereas when you're doing small files, it's lots of little back and forth ping pong from the metadata server. So that's sort of the nature.
And for reads, for lots of little files.
So the file data is always stored in the object store. So if you
Well, actually, but the other issue though also, if you're reading lots of small files like a web hosting load or something
right.
like that, you're going to probably going to get decent response from your you've got metadata issues there too, so those will perform.
Yeah, so hopefully, I mean, if they're warm files, then the client will hopefully have most of its metadata or the data even cached. But if not, then it'll go to the metadata server. The metadata server will have a cache, and if not, it'll go to the disk. But when you actually read the file contents, if it's not in the client cache, it has to go to the OSD, and those files are going to be randomly distributed. So it's sort of a double-edged sword. On one hand, all your I/O is randomly scattered across this huge cluster, so you have 10,000 disks or whatever at your disposal. So fast. On the other hand, if you have like 4 files that are always read at the same time, you're still going to hit 4 random servers. So it's not necessarily efficient.
Okay, and so when you're using the file system layer, the client is doing some caching as well.
Yeah, so it'll use the normal page cache, right?
Cool.
And it coordinates with the metadata server to make sure that its cache is consistent. So
And that's tunable as well, so you can make it check more or less?
No, it's correct. It's not tunable.
Okay.
So NFS, you set a timeout, how long when you read something, it'll just assume it's not going to change for 60 seconds.
Yeah.
Ceph will actually have a lease on the data, and if somebody goes to write it, the metadata server will revoke the lease and then validate that data, and then write it. And when you read it, you won't get that stale data.
So the,
it's not-
so the metadata server lets the client know that this file's changed,
Right.
or that the attributes of this file changed.
Right, or it tells it that its copy is no longer valid, and then it changes it. Yeah,
It's a kind of a push.
it's a callback. It's all message passing.
One of the problems we're running into now is you see NFS just blocks. You know, if someone's just writing tons of tiny files or, you know, doing tons of I/O on the cluster, you know, the entire cluster kind of pauses.
Yeah.
Does Ceph tend to handle, how does Ceph handle that versus NFS? And where am I going to see those bottlenecks? And if I'm hearing you correctly, if I run into those bottlenecks, I just add more to whatever part of the system I'm seeing those bottlenecks.
So the real difference is that instead of having one server that gets blocked up or congested, you have 100 servers. And so if one of those 100 servers gets congested, then 1/100th of your IOs will get slowed down, but the other 99 will be fine. So for example, if it's small files, usually it's like one user shoveling data into the system. If they're on one metadata server, then that one metadata server is going to go slow and the other one's going to be fine. Until the cluster redistributes it across the whole cluster, all the nodes, and then they'll all go equally slow or whatever. It depends on what you're, you have a basic balance between this much work to be done and this many servers to do it. And you either, so one of the interesting things when I was doing sort of the initial metadata server work and figuring out how to make the load balancer work is that trying to measure how well I was doing. The obvious thing is to measure total cluster throughput. But it actually turns out that you can get the highest throughput numbers if you take, if you take a small amount of the workload, the working set, and you distribute it across all nodes and let them operate at like maximum efficiency and then make everyone else go really slow, then you can have insane throughput numbers. But it's totally unfair because some of your work is going crazy fast and some of it's going crazy slow. But if you actually evenly distribute the workload, then everybody sort of like has equally mediocre performance. So it's not very, it's kind of depressing, but it's actually, presumably you want fairness, I guess.
Well, and that's
So that's
exactly
right.
the situation I'm in here.
Yeah.
I would rather have equally mediocre performance because it never fails that one person, eats all of the throughput and
Yeah.
everybody's screwed.
Right.
It's
So,
those 1%ers.
Exactly.
yeah. So there isn't a whole lot of like special handling to like arbitrate and make sure everything is fair. But overall the architecture sort of lends itself towards that. So there's a lot of work to be done as far as performance tuning. So don't expect it to be perfect just yet. Yes.
You might have covered this, but my apologies. If somebody was connected to the system with a client, such as Mac OS 10 or Windows using either Samba or Helios or one of those, would compared to XFS alone, or as compared to XFS with Ceph, would we notice a difference in the transfer rate between the server and the workstation?
So XFS is a single node file system. So if you're comparing a single node running just XFS versus a single node Ceph cluster on top of XFS.
Well, okay, that was my understanding, is that your computer in slide 3, I believe it was.
You can start at 1. Yes, you can do that. Right. It'll be slower because the data is being copied multiple times and all your I/O is going through a metadata server that's been. But if you're just doing like raw I/O through or whatever.
Raw I/O with extreme speed and extremely low latency. What is going to happen in these circumstances? Will Ceph even play a part?
I mean, there is overhead because it is doing something. In general, though, you're usually limited by the throughput on your network, is what we typically found. And most people are using like, well, it really depends on what your hardware is, right? So
Well,
most of our
I would
deployments are
take
using
you with general phrase.
2 gig or whatever, then it's going to be 200 megs a second, right? Assuming you have enough disks behind that.
I'm going way past 200 gigs.
On 2 gig, oh, you're doing 10 gig, sorry.
10 gig,
10 gig, yeah. Okay, that's
way faster.
So we haven't done any performance testing on 10 gig yet. There was a group in Germany that was they were doing an RBT setup. These numbers are, sorry, this is like 6 or 9 months ago. So they were doing an RBT cluster spread across 2 different data centers with 10 gig link between them, so they're multi-site. And they were running virtual machines, running Cameo and the RBT glue, and they were getting 500 or 600 megs per second inside the virtual machine across data centers.
Well, okay, could I ask, is there a way to use Ceph to balance do what Ceph does, kind of sneak underneath Ceph, to the file system itself for the connection to the workstation? Is there any way to possibly?
So if you're using the Ceph file system, when it stores it on the local disk, it looks totally different. It's objects that are named all weird. So you're not going to be able to sneak underneath it.
Okay.
Yeah.
I kind of figured, but I just thought I would.
But if you SSH into one of the OSD boxes and you CD into the Btrfs, what does it look like?
You'll see some FSID file will be a current directory, and inside the current directory, you'll have a directory for each placement group, and inside each placement group directory, you'll have a bunch of files which are the objects. And they might be nested, a mesh of subdirectories.
And is the object file name, does that match up with the object ID?
No, it's the inode number dot and the block number.
Okay, so the block stuff is hidden way down there.
Yeah, so the metadata server has the mapping in the directory of the names to inodes, essentially.
For testing, can you run the metadata server and the OSD on the same box?
Yeah, so most of our development is done, we have a script in the repository called vstart that starts up 3 metadata servers, an OSD, 3 monitors on the same node in the current directory. So they're just daemons. They don't do anything magic. And then you can run, you can mount it with views, you could have a KVM instance that mounts it, or you can deploy it on 100 servers. Or one of the things we're working on right now is Ceph cookbooks to manage the deployment and management, automatically replacing disks and all like that.
Don't forget Puppet too.
Yeah. We haven't done any Puppet work, but.
Would it be possible to take a HPC cluster and triple purpose the nodes for metadata storage and compute?
Yeah.
Are you guys are trying to support that, or is that?
You can run it however you want. They're just daemons. The thing to keep in mind is that the OSDs just need disk, as much disk as you can give them, and the metadata servers just need RAM.
Okay.
And so you don't necessarily want to put them on the same nodes, and you don't usually want, if you have say a 100-node cluster, you probably only want to have like 3 or 4 metadata servers, depending on your workload.
On the OSDs though, Btrfs will use the RAM cache too.
Right.
So you could get some hits. The other one is your metadata nodes, you could even make them diskless clients.
Exactly, yeah. So probably your metadata servers would be just a big fast machine with like 64 gigs of RAM and a boot disk.
Yeah.
And a fast network.
So can you get away with dual purposing compute nodes and storage?
So like running Hadoop or something, or on HPC cluster, right?
Yeah.
That's what you said. Sort of. So there's the thing to watch out for is there's a sort of fundamental problem with I'm assuming you're using Linux. I don't know if the same issue exists on Solaris, but if you have a local file system mounted, that's a network file system mounted on the current node that's talking to a server that's on the same node, and you have to have a heavy workload, the system can deadlock. Because when it gets into a low memory situation, the kernel says, oh, I have all this dirty metadata that I need to write out to the server. And so new allocations wait for that data to get written out. But that data is being written over the network to a user space process that's on the same node that's trying to allocate memory to actually service the request.
Is it possible to get out of that one? Or?
There are hacks that people have done to like flag the process as having a higher priority. that kind of works. If you're using a fuse, the fuse limits the amount of write-back I that's in progress, and so that sort of works around it.
You see people
But it's
doing
not.
that as a use case?
I'm sure people would want to do that. One thing you can do is run your compute workload in a virtual machine. And then the virtual machine is another user space process that's competing on the same level as the server. That'll help. If you're doing Hadoop, if it's like a Hadoop cluster,
Nope.
okay. But if it were, Hadoop is also a user space process, and you can use the user space client, which doesn't have any of these limitations. So, yeah.
So if a node fails, when it's time for it to come back and receive the new data, is that done transactionally, like a series of diffs, or is it done all at once, like here's the data?
It's a series of diffs. So for each of these placement groups, collections of objects, there's internally it's keeping a log of all the operations in that group, and they're all versioned, all the objects are versioned and so forth. So if a node goes down, and then you're writing to the other replicas, and it comes back 2 minutes later after a reboot, it'll just look at that log and say, these are the 100 objects that have changed, and it'll sync just those.
So you can do a node partial recovery. It doesn't have to resync from scratch.
Right. And the other thing that's key is that the replication is declustered, is the term that people use. So if you have, each node has, say, 100 placement groups, and each of those placement groups is replicated on other nodes. If that node fails, then all the copies of those placement groups are randomly scattered on 100 other nodes. And when it re-replicates those to new locations, those new replicas will be on 100 other nodes. And so you basically have the whole cluster going all to all in parallel recovering that data. So it'll take one 100th of the time, in theory, to recover, as opposed to having one disk that has to copy linearly to a whole new. Yeah.
How do you shut it down? I mean,
Kill.
there's inherent recovery, right? So like you can't just go shut down the server and shut down the next one, and
Yeah. I mean,
is there any way to just
turn it off.
bias everything and just go, hey, we need to power it down?
Kill it.
PG&E is coming and cutting the power or whatever.
The easiest thing is to just kill it. PDSH-A, kill all, Ceph OSD, whatever, just kill them all. Because the whole point is that they can fail and restart and they're fine.
Yeah.
So there actually
So there's
isn't.
no way to stop
For most of the daemons, there isn't. For some of them there is, but for most of the time there isn't a clean shutdown procedure. You just stop them.
So when it restarts, it has to scan the node itself. Does it have to kind of scan, hey, here's what I got, and now I'm going to go to the rest of
It's
it?
only at a very shallow depth. So the node will say, I have these 100 placement groups.
Okay.
What are the version numbers for these placement
Oh,
groups?
okay.
And what are the
So it's a
log
higher
numbers?
level, okay.
It doesn't have to scan all 1 million objects.
And then as it checks in, it may have to dig down
Yeah.
deeper or what have you.
So what will actually happen is the node, the OSD, for example, will start up. So I have these 100 placement groups. It'll recalculate, well, it'll get the new latest OSD map. It'll calculate where all those OSD placement groups are supposed to be stored, and it'll talk to those servers and say, this is the latest version, this is what I have, what do you have? Who's the primary copy now? Should I copy anything? What do you want? Whatever. That's that.
Like for your production implementation, what distribution are you going for? Where's most of the development happening? Which Linux distros? CentOS or?
We use Debian.
Okay.
So we use Debian and Ubuntu stuff. I'm an RPM idiot for the most part, so but most people use CentOS, I guess.
On a small scale, would there be any practical reason if you had real limited needs and you had one file server to run this on one file server rather than just run Butterfs and use it with NFS? What would your main gains be, if any?
Not really.
Any reliability gains or feature gains in that?
No, it'll just complicate things.
Yeah, but-
There's more possibility for bugs.
But I guess the interesting is as you scale up, you can either add more OSD
Yeah.
nodes if you
Yeah.
need storage,
If you plan on it to grow later, then it'll.
or if, say, you have a lot of small files or you're having heavy metadata hit, you can add more metadata.
Yeah. So the metadata server does do some interesting things that local file systems don't. One is the recursive M-time thing, which is pretty cool. One is that the inodes are embedded in the directories that reference them, because most inodes only have one link. Usually, I only have one file name to one file. And so things like ls-al that on fragmented file systems go really slow, don't
Yeah.
go slow.
Oh, really?
So that's,
So like, so if you've got the, how has your testing been with the directory with the, 6 million files on it? How does it handle that?
once the directory gets really big, then
Because
you have
people
to,
do that.
yeah. I know. At that point, you have to fragment the file, so the file gets broken into little pieces
Yeah.
that are sort of stored independently, and so you'll sort of iterate over each individual piece. And so that process is slower when you're actually creating the files. But once it's actually there and fragmented, and you're just scanning it, then
Yeah,
it'll be
to
fast.
do that LSAL, how long is the lag
Then
for
it's
that?
on the order of the number of fragments. Basically, each fragment, you have to load it off disk. So that's one big I have to read that megabyte chunk or whatever. And then you get the bounding on the end. So it'll go way faster than normal file. But there are also other things that are doing a lot more work than you otherwise would be. So on the whole, probably slower.
Question, what kind of visibility do you have in the sense of, if I have a RAID file system with 3 disks and I lose 1 disk, I know I'm okay. I know if I lose another disk, I'm screwed. So what kind of visibility do we have when we have a large cluster of a lot of systems to know how vulnerable we are, how degraded we are?
There's so the monitor is, all the OSDs are sort of feeding information back to the monitor, and there's a command line utility called Ceph, and you can do -w, and it'll just sort of give you a rolling update of cluster state, and it'll tell you the state of all the placement groups. So it'll say, 8,000 of them are active and clean, and 100 of them are active and degraded, and it'll give you the percentage of objects that have less than the correct number of copies, for example.
Well, they're
So you can
not
sort of-
meeting those crush rules, right, or whatever?
Yeah, they just don't have, if they're supposed to be replicated 3 times and we only
Yeah.
have 2 replicas, it'll say, n% have this. So you can sort of watch your cluster state that way.
So it'll give you will it give you a clean, clear picture of how urgent, how bad a situation you're in when you've had a number of failures?
Yeah, what happens if
It's
you're,
not
you're-
super-
What kind of interpretation would you need?
It's not like color coded.
You'd have, well, that's a shame.
It's a little bit obtuse to parse the output, but all the information is there, so it really just needs like somebody with more UX experience than me to.
There's no kind of GUI visualization right now, right? Or web-based?
There is a GUI tool that a student wrote that works, but is not very useful. So
Yeah,
the hope is that somebody will just say, "That's great, I want to make it do this," and then they'll add it to that.
because in some failure modes, you may want to know, you may have multiple systems fail, but how do you know when you're getting close to data loss versus, well, and that's just when your replications get to 1 or...
Yeah.
Does,
That doesn't give you.
does this function kind of like a giant RAID set in the sense, a single giant RAID set in the sense of once you've lost all your parity, you lose 1 disk and everything is gone? Or does it function in the sense that you can be degraded to the extent where you've lost data, but you haven't lost all your data?
Right, so data loss will happen at the granularity of an object or a placement group, typically. And
So if that object is
that'll be
one
some
giant file
random
system.
subset of all objects are gone, which isn't necessarily that much better than losing everything. But I really want no data loss.
Well, if it's like an image or something, right, you may
Yeah.
be able to lose parts of the image.
Yeah.
But Ceph will serve up whatever it
Left.
can.
Yeah, if it can, yeah.
And what if the node comes back, say you
If it eventually,
You
if
put an object out with a
reference
copy of
to
2, you
that.
lost both nodes, or they both crashed at the same time, right?
Yeah.
And that object is part of some bigger file. You
Okay.
could still read back the file incompletely,
Yeah, yeah.
and when one of those nodes came back on, is it ever like failed out, unless the file system layer deletes the file.
The administrator, the system basically never gives up. The administrator has to go in at some point and say, this node is lost. There's no way I can rescue that data, and the system will say, okay, and it'll say these objects are now lost. And it'll actually still keep track of them. And so if you try to access them, it'll give you...
But it knows that the data for those objects will never return.
Right. It gives up trying to find it.
But the system has to say,
Yeah.
this server is telling
Yeah,
us.
it doesn't want to doesn't want to give up.
Cool, well, that's great. I mean, because sometimes with the automated things, you get false positives.
Yeah.
And then that can force other kind of cleanup things that could cause data loss when that's not necessarily the case. So that's not a bad way to be.
So is there a concept of, would it be sensible to have a hot spare server if you were going to have a large cluster? Or would that really be nonsensical because the whole system would be more reliable if you just had all of your
Right.
resources?
So the idea is that every server is a hot spare. So if a node fails, then that work is redistributed among the remaining servers.
Is that going to slow things down a lot while it's busy redistributing that among all the other servers? Would it be more sensible to have a single node that can simply replace the entire node that's lost?
Or
But
have a
you
reserve.
would need to get that data from somewhere, though.
Right.
So
It's
I
a
think
question of whether or not it's going to have to
essentially-
reshuffle everything.
So
twice.
say you lose a node's worth of data. So if you need to recover that node's worth of data, either you have a single machine that's trying to copy, a terabyte or whatever from 100 different other places, or you have 100 other locations that are copying 10 gigs from 100 locations. And that'll actually go way faster. So it actually turns into a reliable thing. Once you start crunching the numbers, your probability of data loss goes up if you have a single node that's a bottleneck for recovery. That's actually one of the reasons why RAID systems have to go to RAID 6 multiple parities or whatever, because the time it takes to recover a single disk is just too long that the probability of having a second failure goes up. But by distributing that work across the whole cluster, then you can minimize the impact.
Sure.
But then it's just a matter of prioritizing, right? You have to make the code say, I'm going to dedicate 70% of my resources to ongoing operations and 30% to recovery, or whatever you set that at.
Has this only been tested and is it only intended to be used on a local network where all of these?
Yeah, it's really for a local.
It's not a
single
cross-internet file system.
Yeah.
Have you guys done any experimenting with high latency?
We haven't. Some people have, but usually with low latency links. It's just not designed for high latency links. It's going to be slow.
Have you done any profiling on network load?
On what?
Network load?
Not a lot.
Would there be by the design of it, any kind of logical loss in efficiency because it's clustered over if we're having one giant NFS server that, is it going to be by definition less efficient? It has to keep
So there's,
forward.
by definition, it's a network file system, so you have to talk to the network, so it's always going to be slower than a local file system. And by definition, all the data is replicated n times, 2, maybe, hopefully 3, and so you're going to use 3 times as much disk space. It doesn't do parity. By definition, when you do a write, it writes to all replicas before it replies, and so there's going to be a higher latency for writes. But at the same, and what you get for that then is that you have the aggregate throughput of the entire cluster at your disposal. So, yeah.
Convergence back to a stable, well-distributed system after an error is going to go faster with the large cluster than with the small? Because the
Say that again,
workloads are
convergence?
further.
Convergence what?
To converge back to every object is where it should be after failure, or when you bring something new online. That reshuffling time is going to be lower in a large cluster or a small cluster?
It depends on how much data needs to move. So if you have a large cluster and one node fails, recovery is going to be fast because you have a small amount of data moving between a large number of nodes. If you have a 2-node cluster, or 3-node cluster, say, and you lose one node, then like half the data in the cluster has to move, so that's going to be much slower.
Bigger is better.
That's what they say.
And also, since some of the, if I understand correctly, the location of the data is kind of computed via the map at the time, I guess, that the file was written out or what have you.
Right.
I take it it's better, like if you to add, have as many nodes as you can up front, or do you get a kind of lumpy distribution?
It doesn't matter.
Say you start with 10 nodes, and then a year from now you're down to 90 nodes. Well, do things get redistributed?
Yeah. So if I have 10 nodes and I add 1, then 10% of the data is going to move to that node.
And how does that happen?
It always rebalances.
How do they start balancing the load amongst themselves?
When you add, so the crush function is taking a number and the set of nodes and it's mapping it sort of pseudo-randomly.
Yeah.
So when you add that 11th node, then suddenly 1/10 of those inputs, if you were to recalculate the mapping, was now mapped to that other output.
So and that happens when when the new map is pushed out or whatever. So does each node say, oh, I should have this object now and I don't?
Yeah, well, it's on the granularity of placement group. so that it doesn't have to calculate 1,000,000 mappings, it calculates 100. But yes, exactly. So when it gets a new map update, it recalculates the mapping for every group that it has, and it checks to see if it still has it or if it should go somewhere else.
So it's new map comes in, hey, what placement groups am I in? And then let me go get the things that I'm missing.
Right, exactly.
So it's the node, all the nodes pull, and that's triggered by the map change.
Exactly, yes. Yep.
Cool.
Yeah. So all the you would issue a command that says OSD down, or say OSD forwards down. That would tell the monitor to update the map, and it would tell one OSD maybe, and then they would just start, that map update would propagate throughout the cluster, and they would start talking to each other, and they would just start shuffling data, and you'd see all the disk bytes light up.
All the affected placement groups nodes would start grabbing their stuff. Interesting.
See?
Yeah.
So is the number of placement groups set when you create the cluster initially?
You set it when you create the cluster, but you can change it. So the sort of the rule of thumb you don't want too many placement groups, because if you have a really large number of placement groups, that means that every node is sharing data with every other node, which means that any simultaneous failure means that you lose all the rest. So you want to kind of limit the number, but at the same time you want a larger number because that gives you better balancing. If you have two groups per node, then it's going to be totally irregular usage. So it picks a number out of a hat, basically, when you generate the cluster based on the number of nodes for that at the current time. And then as you grow the cluster, you can split them. So you can adjust it, and they'll get broken in half and then redistributed. The whole process.
It said something about masking, so it's up to.
Yeah, so it uses, it's called like a stable mod function. It's like a modulo function, but it sort of is at the granularity of powers of 2. And so if you have something that's between 2 powers of 2, it isn't a perfect distribution, but it doesn't reshuffle. It's like, think of it as powers of 2, but it sort of rounds things off.
So what happens, let's say, across the cluster at 66% capacity, or let's call it 2/3 to make it easy, and someone, to be funny, decides to shut off the other third of those systems, plus one additional system, which takes you just below that 2/3 mark. How does the cluster handle that?
If you're shutting off the OSD nodes?
Yes.
Or
so let's just say hypothetically, 1/3 of the cluster just disappeared, and I was at 66% capacity already.
Okay.
Does it bump to 100% and then die, or?
Yeah, at some point when it's migrating data, it'll say I need to replicate this data, but I don't have space, and so it'll stop. So at the moment, it'll probably crash. I think is what'll happen.
Okay.
But what it should do is stop replicating data at that point. Basically, it's an untenable situation. Like you can't. There's nothing you can do.
Well, doesn't it send an automatic order to a supplier of disk drives and have them automatically send to it and make new pools and bill your purchase?
I was going to say, send an email to the students, go put another record block in there. Another system.
Generate an invoice.
Exactly.
Yeah.
It's expensive to keep multiple complete copies of your data. Is there any intention to do a parity concept in this?
There was a lot of whiteboarding that went on as far as how that would work. Probably, and realistically, it probably isn't going to happen anytime soon.
What kind of cool, sexy new features can we expect after this phase you say you're in right now to stabilize?
Let's see. Writable snapshots on RVD, writable snapshots on the file system, asynchronous mirroring. So you can say, I want a mirror of the file system that can be up to 10 minutes delayed, and it'll handle that concurrently. Multi-site replication. That's what most people ask for. It's funny, everybody always asks if you can have a file system that spans multiple sites. In reality, I think it's a very small number of people who actually can use it or need it. But that's what everybody asks. That's what everybody wants. So.
Now, and what about backing up? Now, is the multi-site, is that two different Ceph implementations?
I mean, yeah, it doesn't exist.
So that's the theory. And what about, like, you're getting ready to do an implementation, do you have an external backup strategy, or are you just looking to make sure you have enough redundancy in the main system?
I think when the goal is that when you're building systems this big, they're so big that you can't afford to have a second copy, and so that's why you build redundancy into the system itself. At this stage of development, you do want to back up because your source of failure is going to be software failure and not hardware failure necessarily. So now you want backups, but eventually the whole point is that you wouldn't need it. You build a system to be robust and self-healing.
Well, it's still where it's that the cross-site replication thing may be that sort of solution.
If you lose the data center goes offline, then you'll
so that's got to be built. Well, I guess that's about it. I mean, that's a pretty good. I think we had a good 40 minutes of Q&A there.
There's a website. Check it out. And we are always looking for developers, administrators, QA people, that want to work on open source and get paid for it.
Just one last question. What's the biggest known deployment that you guys know about?
The biggest deployment that I know of in the past was the one I did on one of Lawrence Livermore's clusters for my thesis, and that was 400 nodes, but it was 128 metadata servers and then 256 OSDs that were storing just metadata. I was simulating just the metadata workload, so there were like no files essentially. So that would be like the equivalent of like 1,000 or 2,000 nodes, whatever. Currently, there's a 96 node cluster Sandia. Our internal cluster is probably like 50 nodes or something, but they're not 7 disks in each node, and so it's actually like 200 OSDs. But there aren't a lot of like active clusters that are big right now. So a lot of people will like test it on their cluster and then they'll wait for it to scale.
And you'll most likely be speaking in scale again, hopefully, so that we can touch base.
Hopefully, yeah.
Again, that would be cool. And then you're also always welcome to speak here at UAC anytime. All right, hey, so I think we're about done here. So.